Okay, thank you so much for joining us for this week's One World seminar on the mathematics of machine learning. It is my great pleasure to welcome Zhengdao Chen from the Courant Institute, where he is a PhD student. And he's going to talk about a dynamical central limit theorem for shallow neural networks today. Thank you.
All right. Thank you, Stefan, for introducing me and, of course, for the invitation. It's a real pleasure to be able to speak here about our work. This is a joint project with Grant Roscoff, Johan Bruna, and Eric Van den Eyden. So, as we probably all know, neural networks work pretty well in many problems in practice, and in particular, they can be usually well optimized by some gradient-based methods, say gradient descent or stochastic gradient descent. And this might seem surprising because obviously the loss function is highly non-convex in the parameters. So, well, to understand this contrast, one way that people have proposed is to take the infinite width limits of the neural networks and show that in these limits, the optimization actually have guarantees to converge to global minimizers. So there are two such limits that are particularly interesting: the neural tangent kernel or NTK limit, or the mean field limit. So the difference results from different scaling of the parameters as you take the limit. And it has been shown that the mean field limit is, say, better at characterizing the active learning or feature learning that you see in neural networks. Although on the other hand, it's also considerably harder to analyze. So for example, for the NTK, you can derive global convergence results for networks with arbitrary number of layers and even with architectures like convolutions. Whereas for the mean field limit, most of the earlier results only consider shallow neural networks or two-layer neural networks, although there have been recent efforts to extend the analysis to multi-layer networks as well. So now that we have these nice results for convergence in the infinite width limits, in order for them to be useful for our study of finite width networks, we need to somehow quantify the deviation between the shallow models and the finite width shallow models, the finite width models and the infinite width limits. So in the NK limit, this has been done in, for example, the early work of Du et al., which already gave guarantees for overparameterized but finite width networks in the NTK scaling. In this work, I will focus on the mean field limit, and only for shallow or two-layer or one-hidden layer neural networks, which is already not trivial. So as I mentioned, I want to study the deviation between the finite width network and the mean field limit. And it turns out that at initialization, this is pretty easy if we just sample the parameters IID from some underlying distribution, because the deviation just follows the central limit theorem, and it has a variance that decays as 1 over the width you take width to infinity. But the question becomes non-trivial once you consider training. That is how the deviation will evolve as you train the network. This is not obvious because the training will introduce interactions among the parameters. And so their joint distribution will no longer be, say, a product measure. There have been existing bounds, for example, in the early work of May et al., that give bounds on this deviation, but they grow exponentially in the training time. And so they're not sufficiently satisfying if we were interested in the long-term behavior of the deviation, say near the very end of training. And so the goal of this project is to quantitatively study the long-time behavior of this deviation, for which we'll need a finer analysis of the evolution of the dynamics, its interplay, the interplay between approximation and optimization. Okay, so the setup we're considering is fairly simple, which is function fitting supervised regression. So say we're given a target function, call it f star, that we want to fit. So it takes an input from some input data space, capital omega, and it outputs just a scalar. And we're given a set of n training data points, and as well as their labels given by this target function. And the approach we take is to minimize the empirical risk, for which we use the mean squared error here, which is the difference between the fitted function and the fit function squared and averaged across the training data. So to have a more compact notation, we introduce this empirical data measure nu hat, which is the average of the direct deltas at the location of the data points, so that we can write this quadratic loss as an integral over this empirical data measure. The factor 1/2 is just for simplifying the notations later. And so notice that there's no regularization term here for the simplicity of the presentation, but it actually works when we add a regularization. And in fact, I will give results that are more suitable for the regularized cases. Okay. So this is how I will represent a shallow neural network. So M is the width here. So here I should mention that if you happen to be reading our paper on archive, I'm using a different notation here, where I'm using M instead of N as the width of the network, and N instead of L for the number of data points. Apologize for this confusion. Hopefully we will update the archive version with this new notation very soon. So notice that there's a 1/m factor in front, and this is for the sake of taking for getting the mean field limit as we take M to infinity. So I use the zi's to represent the first layer parameters, and ci's to represent the second layer parameters, which are just scalars, and phi hat to be a nonlinear unit. So this will include the case of a usual neural network, for example, in which case phi hat will be a point-wise nonlinear function sigma applied to an inner product between the data vector and a weight vector plus a bias term. So we'll actually introduce a more compact notation by letting theta I to be the concatenation of ci and zi, the second and first layer parameters, and also define phi based on phi hat accordingly. So the reason we do this is that, first of all, this is more compact to write, and secondly, this representation actually gives a slightly more general type of models. And so, in fact, most of the results, most except for two of the results I will mention today, will apply to this more general type of models. And so, for the rest of the talk, I will sometimes refer to the theta i's as the neurons in the model. And throughout this presentation, I will assume that the data space omega is compact, and d hat, which is the space z's live in, is a subset of a Euclidean space, and also phi is twice differentiable with second derivative being Lipschitz. So for example, ReLU wouldn't exactly work here, although there have been like different differentiable approximations of ReLU that I will not go into in detail here. Okay, so now that we write the shallow neural network in this way, as I mentioned, we will train it by optimizing, by adjusting the parameters in order to minimize the loss function. And the way people usually do this in practice is to first sample the parameters IID from some underlying measure on the parameter space that I call mu0 here. So that's at initialization. And then we train it by some gradient method based on the loss function. So these methods could include, say, gradient descent or stochastic gradient descent, which means we update the parameters in the negative gradient direction with respect to either the loss function of the full batch of the training data set or, say, a mini batch. So we do not consider mini batch here, so only gradient descent and not stochastic gradient descent. And moreover, we will take the step size to be infinitesimal, which gives you the limit in gradient flow. So notice that that's a factor of m multiplying on the right-hand side here. This is so that the right-hand side will have a non-trivial limit as you take m to infinity. So as I mentioned, to try to explain why gradient methods usually work well, despite the fact that the loss functions are apparently non-convex in the parameters, people have proposed to go into the infinite width mean field limit. So to introduce the mean field limit, let me first introduce an equivalent way of writing the neural network function using the empirical measure of the parameters. So the empirical measure is just an average of the direct deltas located at the actual locations of the parameters. In this way, we turn the sum into an integral. And also, the gradient flow dynamics in the parameters can be translated into the following dynamics on the empirical measures, which is a Wasserstein gradient flow. So to better understand this connection, let's start from the gradient flow equation and expand the right-hand side, the gradient of the loss. So we can write it in this way, where we introduce two functions, capital F and capital K. So both of them depend on the nonlinear unit phi and also the data distribution nu hat. And also F also depends on the target function F star. So next we also introduce an object V here. So V can be interpreted as a potential on the parameter space. So in the end, this equation says that the parameters will be updated in according to the gradient of the potential V. But instead of being a fixed potential, the V here will actually depend on the configuration of all the parameters, which is represented by mu Tm here. So this is gradient flow dynamics. And we will see that this is equivalent to the following equation for the empirical measures. So this is a measure-valued partial differential equation, and people have called it McKean-Vlasov equation or nonlinear Liouville equation. So it may not be obvious what it looks, what it means from this equation, but we can understand it intuitively as saying that the empirical measure at time t, mu Tm, is a push forward of the empirical measure at time 0 under a characteristic flow map, which I denote by capital theta Tm here. So the characteristic flow map for each t is a map from the domain D, which is the space in which theta lives in, to itself. And its evolution follows this set of equations. As you can see, this is basically the same differential equation as the equation for gradient flow shown above. And so it's actually, we can actually see that they describe the completely equivalent dynamics. To visualize this a little bit better, I drew a little picture. So this is, say, the example of having E being just a line segment. And if we look at the gradient flow, the blue curves indicate the trajectories taken by two neurons under this gradient flow from time 0 to time capital T. And then the characteristic flow maps, the capital theta Tm here, they are just maps from initial locations of the neurons to their trajectories over time when they evolve under the gradient flow of this potential. So one thing is that the characteristic flow map is defined not only on the positions of existing neurons at initialization, but also on the full space D. So when it is applied to, say, a location theta hat that is not on the support of the empirical measure at initialization, meaning that not where a neuron actually lives. So it gives a trajectory of a hypothetical test neuron if it follows under the gradient flow dynamics according to this potential. And then the evolution of the empirical measure is just a push forward under this characteristic flow, as you can see from the figure below here. So it turns out that this is a Wasserstein gradient flow according to a loss functional or energy functional on the space of measures is exactly the same as the loss function on the parameters. So here's a little summary of these two perspectives of looking at things which are completely equivalent. One is to look at things in the parameter space, and the other is to focusing on the empirical measure and how it evolves under the Wasserstein gradient flow of the loss functional curly L here. By the way, I forgot to mention that please feel free to jump in if you have any questions at any time. Okay, so now that these are two completely equivalent ways of saying the same thing, why would we use the notation of the empirical measure? So the answer is that it will be pretty simple to take the limit as m goes to infinity in the space of measures. In particular, if, let's say, the parameters at beginning are sampled IID from some underlying measure mu0, then by the law of large numbers, as we take m to infinity, the empirical measure at time 0, mu0m, will converge weakly to the underlying measure mu0. And in fact, as is shown in a series of work in 2018, this law of large number holds not only at initialization time, but also at any finite time during training. So mu tm will weakly to some mu t, and mu t it will evolve under the same set of same PDE. And the difference is that it starts from a different initial condition, that is mu0 instead of mu0m. So I will call the mu t the mean field limit, and the evolution of mu t, I will call it the mean field Wasserstein gradient flow or mean field gradient flow. So similarly, we can also define a characteristic flow for this mean field gradient flow. I'll call it capital theta t, dropping the superscript here. Okay, so here's the illustration. By taking the mean field limit, the empirical measures, which are sums of direct deltas, will converge to something that may have a density over D. And then it will evolve under the same Wasserstein gradient flow, starting from the initial mean field measure. So, okay. So it turns out that things are pretty nice in the mean field limit, in that the same series of work have shown that the mean field Wasserstein gradient flow will converge to global minimizers of the energy functional under certain conditions. So besides some more technical assumptions, we need conditions. We need two conditions here. The first one is that we need to be exactly in the shallow neural network setting. So this is one of the two results I mentioned that will require us to consider the first and second layer parameters separately instead of consider them together. And secondly, we essentially need the initial mean field measure mu0 to have full support in Z, say, as opposed to being singular. So this means that global convergence can only hold in the mean field limit and not for finite with empirical measures. And therefore, in order for this result to be useful for finite width networks, we need to somehow bound the difference between the finite width network and their mean field limit. Okay, so we can see this relation also in this diagram here. So on the top and the bottom row, empirical measure and the mean field measure both evolve under Wasserstein gradient flow. And for each finite time, as m tends to infinity, the empirical measure will converge to the mean field measure by the law of large numbers. And this relation then induces a similar diagram in the space of functions that these measures represent under this the integral representation. So by the global convergence result, we have that the mean field measure, the mean field neural network will evolve to some ft that is, say, close to the target function f star when t is large enough. And therefore, our goal, well, if we want to say something about ftm in the top row, we need to quantify the deviation between FTM and FT. So in some sense, FTM can be considered as a way to approximate FT by first sampling the parameters from F0 and then evolving the parameters under the gradient flow. So we wonder how good this approximation is. So it turns out that, as I was saying, things are pretty easy at initialization time. So we can first introduce this omega Tm, which is the deviation in the measure between the empirical measure mu Tn and mu T. So remember that mu Tm is random here because of the random initialization of the parameters. And so omega Tm is random as well. And this factor square root of m is added so that well, the scale of the randomness has a non-trivial limit as you take m to infinity. So indeed, by the central limit theorem, at time 0, the omega 0 will converge weakly to a random Gaussian measure omega 0, and omega 0 has mean 0 and the following covariance. So this is just a more fancy way of saying that if you take a test function and you integrate it against omega 0, you get a Gaussian random variable with a mean and covariance that is what you would expect from the central limit theorem. So in particular, this means that we can bound the deviation between F0m and F0. So the deviation in the function space represented by the finite width network and the meaningful neural network at initialization. So we will bound its variance averaged across the training data set. And this is this scales inversely proportional to the width m, which is by the central limit theorem scaling. And constant, I call it MC for Monte-Carlo, because it is essentially a Monte-Carlo sampling error, and the error depends on the mean field measure mu0 at initialization. So okay, this roughly says that at time 0, things are well under control. But then the question is how will it evolve during training? And as I mentioned, this is not obvious because training introduces interactions among the parameters. And so if, let's say, we apply a Grunwald's inequality, then indeed we will get a bound that grows exponentially in time, because in a sense we're considering the deviation as a perturbation to the initial mean field measure at initial time, and then this deviation will evolve under this dynamical system. So naively, we only get a bound that grows exponentially in time. So we have to work harder and look at the dynamics if we want to get something that's better. So in the end, we will focus on controlling this quantity here. So we scale it by m because of the 1/m central limit theorem scaling. And we take m to infinity first, so that we're exactly in the central limit theorem regime. And then because we're interested in the long time properties, we will then take time to infinity as well. Okay, so this is what we are hoping to show. Well, the first result is a set of equations that tells you how omega Tm will behave in the m to infinity limit. So we first have that for any finite t, as you take m to infinity, omega Tm will converge weakly to a random measure omega t. And this omega t, it is characterized weakly in the following way. That is, if you integrate a test function chi against omega t, the expression looks like this. So the results like this have been given in the context of interacting particle systems in some fairly classical work like Brown and Hepp. And in the context of neural networks, they have also been given in the later work of Silignano and Spiliopoulos. And our goal would be to use this result to something about the long time property about the deviations. So notice that the important object here is the capital T. So so for each finite T, it is a random vector field on the parameter space T. And it can be intuitively understood as the infinitesimal variation to the characteristic flow map if you perturb the initial measure of the Wasserstein flow from the mean field measure to the empirical measure. So to see this a little bit more concretely, I drew another picture. So here the pink curve gives the characteristic flow map of the mean field Wasserstein gradient flow, and the blue curve gives the characteristic flow map of the empirical Wasserstein gradient flow, both starting from the same position theta. And their difference is the vector field capital T Tm up to a scaling of square root of m. So with this square root of m scaling, it turns out that as we take m to infinity, this Tm will converge to Tt, capital T, which is the object mentioned on the previous page. So here we see that capital Tt lives in the space of random vector fields on D. And this randomness, again, comes from the IID sampling of the parameters at initial time. It turns out that this space of random vector fields is a Hilbert space if we give it the following inner product. That is, given two such vector fields, we take their dot product, integrate it across in space, and then taking the excitation. So once we consider things in this Hilbert space, the dynamics of capital T that is given previously can be rewritten as the following linear ODE in this Hilbert space, where we have defined the ATK and ATV as two linear operators on this Hilbert space, and the B as an element in this Hilbert space, so as a source term to this linear ODE. So this ODE will be important to us later, but for now, let's first go back to the question, our goal, which is to quantify the deviation in the function space. So it will be useful to consider a baseline to compare with, and the baseline is this. So remember that mu Tm is the empirical measure that we evolve under the empirical Wasserstein gradient flow. So so we're interested in the deviation between mu Tm and mu T, and we compare it with following baseline. That is, what if we sample m parameters IID directly from mu T, and we will call the empirical measure obtained this way mu bar Tm. So this is of course this is like a cheating solution, which cannot happen in practice because we don't know how the mean field Wasserstein gradient flow evolves, which is why we have to first sample finite number of parameters and then evolve under the finite particle. But this is a reasonable baseline to compare with, because, well, if we can show that the deviation between mu Tm and mu T is not much worse than the deviation between mu T bar m and mu T, so it's not much worse than cheating, then in some sense we're doing pretty well. And secondly, it turns out that the deviation of this baseline can be expressed quite easily. So we can define f bar Tm and omega T bar and omega bar Tm similarly to ftm and omega Tm, just by replacing mu Tm by mu bar Tm and mu Tm by mu bar Tm. And it turns out that, first of all, omega bar Tm all has a limit as m goes to infinity to omega bar T. And secondly, because we're sampling directly from the mean field measure at time t, so the central limit theorem, standard central limit theorem applies again. And the fluctuation of this ft bar m is also given by a Monte-Carlo sampling error that is that scales inversely proportional to the width m. Okay, so we now have this baseline to compare with, and it has a pretty simple form to analyze. It has a simple expression. Well, to make our life simpler, we will introduce the following two quantities, fluct t and fluct t bar. So both of them are functions on the data space. And for example, fluct t is defined as the difference between the finite width neural network function ftm, the mean field limit ft, and scale by square root of m. And similar for fluct t bar, where we just replace ftm by ft bar m. And firstly, notice that they can both be represented as integrals over omega t and omega t bar, respectively. And then, so with this notation, our goal would simply be to compare fluct t and fluct t bar in their variance and averaged across the training data for large T. Okay, so here's our first attempt at analyzing fluct T and fluct T bar. So actually, immediately from the equation linear ODE for capital T that we saw earlier, we can get the following relation between fluct T and fluct T bar, which is a type of Volterra equation involving time integrals. So roughly speaking, we obtain this simply by using Duhamel's principle on the linear ODE for capital T. So this Volterra equation involves this this object gamma Ts, and which then involves JTS. So how does this help us? Well, we can first consider a simple case as t goes to infinity, or equivalently, we can consider the case where mu0, the initial mean field measure, happens to be a stationary point of the Wasserstein gradient flow, and so it will not evolve anymore. The mean field limit will not evolve anymore. In that case, the Volterra equation has this following simpler form. In particular, it becomes a convolution type Volterra equation with the convolution type Volterra kernel gamma infinity. So if we can show that gamma infinity is positive semi-definite as a convolution type Volterra kernel, then we immediately get the following, which is the average variance of fluct T under this average time integral is upper bounded by the average variance of fluct bar. And because the mean field Wasserstein gradient flow doesn't evolve, so fluct bar infinity is the same as fluct bar 0, and it's given by the same Monte-Carlo sampling error. So this is pretty much what we were hoping for. And then the question is, first, how can we show that gamma infinity is positive semi-definite? And secondly, whether it is sufficient to consider the time asymptotic case. Can we make sure that what happens at time doesn't change the conclusion? So it turns out that we can handle this if we are willing to make the following assumptions. The first one is we assume that the Hessian of the potential V is uniformly positive definite on the support of mu infinity, the limit that is the limiting mean field measure. And the second assumption is that the convergence happens fast enough, basically. So if we're willing to make these two assumptions, then basically the result shown earlier will hold. So regarding the assumption on the positive semi-definite of the Hessian of the potential, we think it may be plausible for the case where we add regularization to the empirical risk, although it's not something that we prove. Okay, so this is what we can get from the Volterra analysis. It turns out if we want to get something stronger and say replace the assumption on the Hessian of V, we need to do a finer direct analysis on the dynamics of capital T. Okay, and let's do this. So recall that we defined these two objects, flux T and flux T bar, in this way as the fluctuations. And we want to compare them against each other, hopefully showing that flux T is controlled by flux T bar. So it turns out that using the expression is the expression as integrals over omega T and omega T bar can relate flux T and flux T bar by the following expression. So the extra term is a term that involves the capital T object. So, and then the question is whether this second term is favorable to us or not, whether it improves the fluctuation or no. So to see this, we can directly take the difference between the average variance of flux T and that of flux T bar, which is quantity that we want to upper bound. So with the inner product introduced previously for the Hilbert space, and also the operator ATK, and also the element VT, we can write the difference in this way. So now this looks quite related to the dynamics of capital T. Because in particular, if we look at the time derivative of the squared norm of capital T in this Hilbert space, it gives the following. And so if we can assume that capital T converges nicely to a limit in the Hilbert space with the time derivative of its square norm converging to 0, then we have the following. It is the sum of these three terms being 0. And we can then use this, plug this into the expression for the difference between flux T and flux T bar as time goes to infinity. And then we will be able to conclude that this is non-positive if we show that A infinity K and A infinity V are both positive semi-definite operators on the Hilbert space. So A infinity K is positive semi-definite simply by expanding what it means. And for A infinity V, we would naturally expect it to be positive semi-definite in order for the characteristic flows to be attracted to their limiting positions. But in any case, if we restrict to the scenario where the mean field dynamics converges to a solution that interpolates the training data, that is, mu infinity and f infinity is such that they agree with the target function f star on the training data points. So this will happen, say, if there's no regularization terms to the loss, and that the mean field dynamics indeed converges to the global minimum. So if this happens, then A infinity V will be 0. And therefore, the relation above will indeed hold. Okay, so this is pretty much what we were hoping for. But the problem is we cannot simply assume that the capital T has a nice limit. And in that case, we can still write things similarly, and we will need to take an integral over time. And the integral of the difference between flux T and flux T bar in this average variance is a sum of 3 expressions. So the first term is non-positive because we start from the T0 that is 0. So this is non-positive. For the second and third term, we will hope to show that they are also non-positive. For this to happen, we will first need that A infinity V and A infinity K be, again, positive semi-definite operator. And secondly, what happens at finite time integrated over all time does not contribute to our final answer. And for this, we will need some assumptions on the convergence rate of the field gradient flow. Okay, so in the end, we summarize this in this result here. That is, if we're in the case where the mean field limit interpolates the training data, and then the convergence is fast enough so that the loss decreases at least quadratically fast, then we will have the following result. That is, the flux t, its variance averaged over training, and under this average time integral, as t goes to infinity, is upper bounded by the average variance of flux t bar as t goes to infinity. So regarding this convergence rate assumption, it may not be something intrinsic to the problem. So it might be that someone can find a weaker assumption or no assumption later. So yeah, this is the result for the interpolation or unregularized case. So back to this the diagram that we showed before. This means that the fluctuation between the fluctuation obtained by taking the red path of having a finite width approximation to mu t is no worse than the blue. So in a sense, what we actually do in practice is no worse than the cheating way of doing it in this asymptotic central limit theorem scaling. So this is pretty encouraging. At least it means it means that we're doing pretty well. Even no worse than, say, no worse than if we even knew the correct mean field measure mu t under gradient flow and then sampling directly from it. And okay, this is encouraging. And I will say a word about what if we do not make the assumption that the mean field dynamics interpolate the training data. So we can also get by if we're willing to assume that the smallest eigenvalue of the Hessian of the potential V becomes positive semi-definite, becomes a non-negative fast enough. And it turns out that in the interpolation case, we can get a stronger result. So, well, if you remember, this is an expression we had previously, and as long as we showed that the three terms on the right-hand side are all non-positive, then we showed that the flux t is controlled by that of flux t bar. It turns out that under two conditions. First, if we're in the shallow neural network setting, and secondly, if the mean field dynamics converges to a solution that interpolates the training data, then the third term over here will be exactly equal to the negative of flux t bar as t goes to infinity. So this will mean that flux t, which is the quantity we're interested in, its average variance will go to zero eventually, which is, of course, a stronger result. And this is summarized here. So this means that the fluctuation will eventually vanish the central limit theorem. We are looking at shallow neural networks, and the mean field limit interpolates the training data. Okay. So it turns out that there is a indirect connection to generalization by function norms. So the previous upper bounds that we obtained for flux t is given by flux t bar, which is then a Monte-Carlo sampling error. And this Monte-Carlo sampling error is closely related to the variation norm or Baron norm of the limiting function. And these norms have been used to give generalization error bounds. So now we have two reasons, one from approximation and one from generalization, to use this term as a regularization term added to the loss function. So finally, I will show some numerical experiments. So the first row corresponds to not having regularization, and the second row is having the regularization term mentioned on the last page. And we can focus on the second column here, where the solid curve plots the fluctuation, the average variance of the fluctuation multiplied by m. So the first thing we see is that for different choices of m, the curves agree pretty well, which mean that the fluctuation indeed remains at the 1/m central limit theorem scaling. And secondly, the curve, they are in a general tendency to decay over time. And for the unregularized case, it will go to 0, or at least close to 0, which is consistent with our with the previous result we had for the unregularized case. And for the regularized case, it will not go to 0, but it remains below this horizontal dashed line here, which gives the Monte-Carlo bound that we had on the right-hand side. So, I mean, because the theoretical results we obtain are only asymptotic in T and M, so we won't be able to say that the numerical experiments confirm the results, but at least they do not look contradicting to our theoretical results. Okay, so in conclusion, we study the deviation between finite width shallow neural networks and their mean field limit. We showed that the deviation remains at the central limit theorem scaling through our training, and that in the long term, the deviation is upper bounded by that of a Monte-Carlo resampling from the mean field measure. And moreover, if we're looking at shallow neural networks and the mean field solution interpolates the training data, the fluctuation will eventually vanish in this central limit theorem scaling. And that is all I'll talk about. Thank you very much for your attention.
Thank you, Zhengdao, so much for this lovely talk. If you've got questions, please feel free to unmute yourselves and ask directly, or if you are in a place where you can't unmute yourself right now, then please just pop them in the chat and one of the organizers will ask them for you. And I think while we want to allow people to unmute themselves, I'd like to ask a question already. Namely, you had this decomposition into a potential and I think a square term. Did you consider did you mostly consider L2 approximation, or did you also think about more general loss functions at some?
Yes, we only considered square loss and not other types of losses. So yes, unfortunately, I won't be able to say anything about other types of loss functions.
And the second question I had is, you say in the interpolating regime where your function exactly fits the training data, do you rely on the fact that you've got finite training data, or does it also work if you've got some target function that you can fit exactly?
Well, so our result for those cases are like based on this assumption of interpolating. So it's a separate question of like whether interpolation will actually happen in the mean field dynamics, and whether it only happens for, say, if you have finite training data or infinite training data. I guess we were saying that if the interpolation happens, then our result will apply. So I think, well, say if you have, whether you have infinite or finite training data, if there's no regularization term, and if you assume that indeed you converge to a global minimizer, then that means that you will you will interpolate the training data, right?
Yeah.
So yeah, all our results are conditioned on this assumption that interpolation indeed happens.
Okay.
Yeah.
Does somebody else have questions? If that is not the case, then I will pursue this point a little bit further. So
yeah.
basically, if you've the estimates are then independent of the number of data points, and you can allow any training data as long as you assume that in the mean field setting you converge to the perfect fitting solution.
Yes. So the dependence on the number of training data points, it could appear in the Monte-Carlo sampling error. Let me see if I can find it. Yeah, say the MC of mu infinity, that will be something that depends on the training data, because it would depend on the functions k and f I define, and those would depend on the training data. It's, yeah, I guess, yeah, so those are sort of hidden over there. And yes, that's pretty much it.
Makes sense. And then the obvious question. So I know that I've looked at multi-layer networks myself. I know that the theory there is a lot more spotty, but do you have any clue? Do you have any clue of what you would need to change? Or any idea of how equations would evolve there?
Well, so that's a very good question, and I don't think I have many ideas of what that will happen. So first, there's a question of what's a correct mean field limit for multi-layer networks. There have been recent efforts of defining that. To be honest, I'm not too confident with saying which ones are the best limits to look at. And so on top of that, we need to study the fluctuation. So that's even one step further. So yeah, unfortunately, I don't have much to say there.
Okay.
Yeah.
All right. If there are no more questions, then I want to thank you again for the lovely talk. And I hope to see everybody again next week.